Guys, this is where we left off, and we were talking about the process of making a set of standards with an internal standard incorporated within. So we said that we would make a set of standards just like always, just like we've always have up to this point. And the only difference here is that we have added in the same volume of an internal standard to each and every one of them. That way the internal standard volume is staying constant. It's a constant value. It's not changing at all. We're putting the same amount in every single one of them. So the question is, why would we do something like this? And then what kind of compound would make a good internal standard? All right, so first, you have to understand that this really is for instrumentation. That's why we use it most of the time. Okay, it's not to check your solution prep. It's not to check your standard sets. We can do that a number of different ways. But internal standards really for the instrumentation that you're going to be using. So if you're running a set of standards on some type of equipment, and this equipment is typically any type of chromatography equipment in particular, you would need to have an internal standard in place. Okay, and here's why. Let's say that I make a set of standards and I have a tray and I put samples into the vials, and we call this an auto sampler tray. And this tray goes over to the machine, and it's all connected with wires and tubing that comes out of the top, and knobs and gears and displays that are on the front. And this tray goes on the inside. And I set up my software, and I tell the machine that I want you to inject all of these samples for me. And then I walk off and I leave that sample and I let it, or that sample tray, and I let the tray get injected over the next 4 or 5 hours, and I come back to it after that is now finished. Well, number one, I've made an assumption. I have assumed that the instrument was working properly. And then I take my data and I have my standards 1, 2, 3, 4, 5. And I have the areas associated with each one of them. And I do a calibration curve. But let's say it looks like this. And I go, uh-oh, I messed up on standard number 4. I need to leave that one out. And then I can draw a linear regression line through the rest of the points. Well, here's the moral of this story. This mess up, it might not be you. That mess up could have been due to the equipment, to the instrumentation. Believe it or not, the instruments are not perfect. And the instruments can have bad days as well. And the instrument might have injected a little bit more for this sample than what you told it to inject. And because more was injected, a higher signal was found for that standard, and maybe you really did do your job the proper way. It's the instrument that messed up here. All right, well, if we don't do internal standards, we would never know this, right? If we just had you make a set of standards and that was it, just one set of standards, and we had you to inject those set of standards, and we called it a day, we would have no clue that the instrument had malfunctioned at any point in time. Now, the calibration set, not too big of a deal, right? It's the standards that would cause a problem, because what if this was a sample? Then we would have a bigger problem, because I would have no clue that this would have been messed up. I would have had no clue that that machine actually injected a little bit more or a little bit less compared to everything else. And my data for my samples depend on those areas, that amount that was injected every single time from the equipment. So for the instrumentation, this is why it's used. The standards, every time we run a piece of equipment, especially in the chromatography world, because almost every single time these have auto samplers. And it's the auto sampler that I am checking here. That's really what we're doing. Each auto sampler has a needle, just like an actual needle that you might have used up to this point to make samples or to inject things with. But that auto sampler has a needle, and this needle can get clogged. This needle can get air bubbles on the inside. The needle can actually malfunction. It might not suck up anything at all. The needle can actually suck up too much at any point in time. You are relying on gears, you're relying on pieces, you're relying on parts in order to do the injection for you. And you are assuming that it's doing it the proper way. When, number two, you cannot assume anything. The instruments, they can malfunction. And the purpose of the internal standard is to look and make sure that the instrument is not malfunctioning in the injection side. That's the whole purpose of the internal standard. Now, there's other reasons to use them, don't get me wrong. There's other reasons to use internal standards, but as an analyst working in a laboratory, this is the biggest reason that we would use an internal standard to ensure that we are injecting the proper amount every single time that that sample goes into the machine. So we're testing the auto sampler. We're testing the instrument for a change. We're not testing you. And that's really the major purpose of an internal standard. Okay? Something that you have to keep in mind is that internal standards are given to standards itself to make a cal curve with. This helps us make sure that we get the best cal curve possible. And the internal standards are also incorporated in the samples. And this is to ensure that we are injecting the proper amount every single time. So the internal standards go to everything. Every single thing that you're processing, every single thing that you're running in that machine gets the internal standard spike or addition. All right, so in the next video, we're going to kind of take a closer look at a internal standard, talk about the proper properties that it should have, and then maybe take a look at an example that we can use and go by to learn how to do these calculations.